Hi everybody, my name is Tej, and today I'll talk about my work on verifying a concurrent file system. File systems are an important but challenging part of an operating system. They're important since essentially all applications rely on them to store their data, but since file systems have sophisticated optimizations for performance reasons, they're also prone to bugs. These bugs can be especially bad in a file system because they can lead to issues like permanent data loss. So in this work, we present DaisyNFS, an implementation of the network file system, or NFS protocol. This is a standard file system API, and our server is compatible with existing clients. But what makes DaisyNFS special is that it comes with a theorem, proven using formal verification, that says that the server correctly implements the NFS protocol. To carry out the proof, we start with the same executable code. We write a specification that captures the intended behavior of the code. And then finally, we write a mathematical proof that shows that the code always meets the specification. For confidence in the proof itself, all of this is carried out in a computer, and a verification tool checks that the proof is valid. The nature of these proofs means that they force the proof engineer to systematically cover every corner case in the code, preventing whole classes of bugs. The proof faces two core challenges. The first is that a file system is generally expected to keep your data safe, even if the system crashes, say due to a power failure or a kernel panic. After a reboot, you expect that your files are still there. The second challenge is concurrency in the implementation. Just as concurrent software is hard to write correctly, it's also hard to verify. DaisyNFS offers a design that makes it easier to scale up verification to something the size of a file system. We split DaisyNFS into two main parts. At the bottom level, we implement a transaction system that makes it easy to get atomicity on top of a disk. And then the file system code on top is implemented entirely using transactions. The transaction system has to face these core challenges of crashes and concurrency, but its proof handles them in such a way that the file system code on top can be verified using much simpler sequential reasoning. A simulation transfer theorem, proven that we developed and proved for the transaction system, captures the verification benefit of transactions. Namely, that we can turn sequential reasoning for the transaction bodies into concurrent and crash-safe correctness for the whole system. So just to show that DaisyNFS is a real file system, I'm going to do a quick demo that was recorded from my laptop. So in this demo, I'm going to run the server in a terminal window. Then I'm going to switch over and use standard macOS tools to connect to this file system the way you'd connect to any other NFS server. I'll add a file to the file system. And now just for fun, I'm going to crash the file system and then restart it. Normally there's no reason to do this, but we have a proof that it's going to handle this correctly. Then I switch back to macOS, and it transparently reconnects, and we can open up this file. OK, so how do we make DaisyNFS work? DaisyNFS has three main layers. At the top level is some unverified code that handles TCP connections and implements the NFS wire protocol. This calls into verified code written in Daphne, which is a verification-oriented programming language that has integrated support for writing this code and writing the proofs. The Daphne code is compiled to Go and then linked with the transaction system. What the transaction system guarantees is that for each of these transactions, all of the reads and writes between begin and commit behave atomically. And that atomicity is in two senses. So first, if the system crashes, either all of the writes will be on disk or none of them will be. And second, other threads only observe the effects of complete transactions. The implementation makes this possible using a combination of journaling to achieve crash atomicity and two-phase locking for concurrency atomicity. So what is DaisyNFS supposed to do? What is the top-level correctness theorem that we prove? To start with, we need a formalization of NFS operations, which we carry out in the form of a transition system. On the slide, I've shown one possible sequence of transitions in that transition system when the user issues vector and lookup concurrently. Due to concurrency and crashes, even these two operations have a few possible executions. But by contrast, the execution of the code on the bottom is much more complicated than that of the specification. For performance reasons, the execution of these two operations will interleave, and the system could also crash at any time in the middle of one of these interleavings. For DaisyNFS to be correct, what that says is every one of these executions at the code level should behave as if the makedir and lookup operations were atomic and followed the NFS spec. And the top-level correctness theorem says this for any combination of concurrent or sequential NFS operations that the user might issue. The way we verify DaisyNFS is primarily by using sequential reasoning for the transaction bodies, because the transaction system makes these transactions appear to run sequentially. The way we do that is using standard sequential verification, a technique called forward simulation. In this approach, we first write an invariant that connects the disk at the GoTxn, the transaction system level, to the abstract state of the NFS server from our formalization of NFS. And then what we need to do for the proof is show that this invariant is maintained by every operations implementation. This reasoning is sequential, and thus it has a lot lower proof overhead compared to reasoning about crashes and concurrency the way we need to do within the transaction system. Now this is just sequential reasoning, so how do we connect this down to the actual transaction system? The way we do that is we prove this simulation transfer theorem. What the theorem says is it has as an input or as an assumption that the user has already proven forward simulation for all of the operations in their system. And then it outputs a concurrent and crash-safe refinement theorem of exactly the style of the DaisyNFS correctness theorem that I showed earlier. Now, the full proof of simulation transfer is a bit involved, but I can give some intuition for why it holds. So for any execution of the code on the bottom, we need to show that there exists some concurrent and atomic execution at the specification level. So the way the proof works is it first uses a lower level specification for GoTxn to show that there exists an atomic execution of the transaction bodies. So this is not yet the specification, but at least they're executing atomically. And then because of this forward simulation, it's a completely standard sequential argument that these behave as the NFS protocol says. Now, I've shown a slightly simplified version of the simulation transfer theorem. An important complication is that it only holds if the program that we're verifying uses the transaction system correctly. And in particular, the theorem includes a requirement that all the shared state in the system has to go through the transaction system, which is kind of intuitive. The transaction system needs to know about all of the shared state so it can actually make things atomic. Now, this poses a challenge in the file system because sometimes you do want to have other shared state. In the file system, the example that comes up is we might want an in-memory allocator in order to improve the performance of allocation. So I'll walk through how we integrate that into GoTxn for DaisyNFS's purposes. So let's consider the pseudocode for write and remove, which are the key places one of the places where we need to allocate for blocks. The in-memory allocator has to be part of the transaction system as shared state, otherwise the system wouldn't be sound. And one plan for making this allocation operations atomic would be to introduce an allocator lock, and then acquire it in the two-phase locking discipline, which means that when we alloc and free, we'll acquire this allocator lock, and then we'll release that lock at the end of each transaction after commit. Now, unfortunately, this plan would be pretty bad for performance because many transactions involve making allocation decisions, and all of those would conflict, greatly reducing concurrency in the system. So our solution to this problem is to first make the allocator efficient by not holding a lock throughout the whole transaction. However, now this is not really an allocation operation. We replace it with this weaker alloc_hint operation. And you can see in this code that alloc_hint, the result of the alloc_hint call is checked against the on-disk allocator state. And that on-disk allocator state is really the source of truth for allocation in the whole system. As a result of making this change from alloc to alloc_hint, we can actually incorporate it soundly into the transaction system. Even though we release a lock early and this doesn't appear to follow the two-phase locking discipline, we're able to still verify simulation transfer just because alloc_hint has a much weaker specification that allows it to return potentially stale allocation decisions. So now I want to turn to some evaluation of DaisyNFS and GoTxn. I'm going to look at three main results in our evaluation. First, I'm going to show that GoTxn reduces the proof burden of verifying DaisyNFS. Then I'll talk about some bugs that we found in the unverified code and specification, things outside some of the trusted code. And then finally, I'm going to show some performance results for DaisyNFS. So the first set of results is we looked at proof burden. So first of all, if you look at the executable code in the system, you can notice that the majority of it is in DaisyNFS, implementing the file system code. But the proof, the vast majority of the proof, is for GoTxn, for this transaction system, verified on top of our prior work called Perennial for verifying concurrent and crash-safe systems. One coarse measure of proof overhead is to look at the ratio of lines of proof to lines of code. And we find that DaisyNFS has a pretty low proof to code ratio, less than 2x, whereas GoTxn is more like 20x. And the result of having this lower proof burden is that it's a lot easier to get to these 4,000 lines of code, add features to cover most of NFS, and to improve the performance of the file system code. So next I want to talk about some bugs that we found. So first of all, I want to emphasize that we didn't find any bugs in the verified parts of DaisyNFS or GoTxn. We didn't run into concurrency or crash bugs. And as a result, the debugging experience was a lot more pleasant here. We could just focus on, when we found bugs, we could just focus on the unverified parts. So first of all, sort of unsurprisingly, we found bugs in our parsers for the NFS wire protocol. These were all pretty simple panics, pretty easy to debug and fix once we found them. More interesting are bugs that we found in the specification itself. And I'm going to talk about one interesting example that comes from the interaction between verified and unverified code. So the code in question involves a type of inode numbers, ino, which uses a Daphne subset type to say that this inode type only consists of inode numbers that are within bounds. When you take an ino as an argument in a method in Daphne, it's slightly subtle because what it actually means is that you're creating an implicit precondition that this inode number passed in is actually bounded. Normally this is okay because it's going to be verified, but in the case of this remove call that I'm showing on the slide, this is actually a problem because it's called directly from unverified Go code. And any precondition in a top-level method in Daphne implicitly is an assumption that all of the unverified code will respect this precondition. And unfortunately, normally preconditions are not necessarily bad, but in this case, this one was unintentional. It was kind of hidden in the syntax of Daphne, and the Go code could actually violate it with a bad NFS request. So we fixed this bug by removing the precondition and replacing it with a verified dynamic check within Daphne. So next I want to talk about performance. So we evaluate the performance of DaisyNFS by comparing against the Linux NFS server. These two file systems are a bit different. DaisyNFS operates directly on top of a disk, whereas the Linux NFS server just exports an existing local file system. So for that file system, we plug in ext4. We run ext4 in this non-default data equals journal mode so that both file systems have comparable crash safety guarantees. But the paper also has results for ext4 in its default data equals ordered mode. We ran the experiments on an Amazon EC2 i3 bare metal instance. This is a fairly beefy storage-heavy machine. We ran on 36 cores and on a very fast NVMe drive. We ran 3 benchmarks. Small file is a metadata-heavy benchmark that creates and deletes a lot of small files. Large file repeatedly appends to a file and grows it to a large size. And the application benchmark here clones a C repository and compiles it. So first I'm going to show throughput numbers for all of these experiments. I'm going to normalize these results are normalized against Linux, so Linux always gets a 1. And we find that DaisyNFS achieves good performance on these single client benchmarks, within 60% that of Linux. And the lower performance in this case is mostly due to less optimized use of the SSD. Linux has a pretty good I/O stack that takes better advantage of the SSD. So these are all with a single client. What about multiple clients? So to evaluate how well DaisyNFS takes advantage of concurrency, we ran the small file benchmark with an increasing number of clients. All of these clients run in separate directories. And then I'm going to show the aggregate throughput for the whole system. And we can see that DaisyNFS can indeed take advantage of multiple clients, although the throughput saturates at some point. DaisyNFS's peak performance is within about 60% that of Linux again. So in this case, the lower performance is because we run into some lock contention with a lot of clients within the GoTxn code. And Linux, by contrast, scales a bit better. There's a lot of work related to DaisyNFS and GoTxn. GoTxn is actually implemented by extending our prior work called GoJournal. So GoJournal was a verified journaling system. But it doesn't do concurrency control for different operations. So GoTxn implements that concurrency control in the form of two-phase locking, and then we verify the two-phase locking on top of the GoJournal spec. FlashX is another verified concurrent file system for flash storage. But FlashX doesn't have anything like transactions to reduce the proof burden. They deal with crashes in concurrency throughout their proof. And then finally is Isotope, which is an unverified file system. But it's also designed with transactions. So there's a transactional layer and then a file system layer on top, although neither are verified. So in conclusion, I've presented DaisyNFS here, a verified concurrent file system that achieves good performance. The key contribution that enables DaisyNFS is the simulation transfer theorem, which captures the verification benefit of transactions, namely that they turn sequential reasoning into concurrent and crash-safe correctness. Thanks, and I'm happy to take questions.